Good evening, everyone present here. So we will wait for 5 minutes. After that, I will start the session. Good evening, everyone present here. Welcome to the third online session of course Wastewater Treatment and Recycling. The course is being taken by Professor Manoj Kumar Tiwari from IIT Kanpur. My name is Manettam Prakash, and I am a PhD scholar in Department of Civil Engineering with a specialization environmental engineering. So this is third week, and every week we meet on Tuesday from 7 p.m. to 9 p.m. and we use Google Meet for our discussion, and the link has been already shared with you, and the recording of this session is being uploaded on this YouTube channel, and the link for which has been also been shared with you. So in week 3, sorry, there is a typo mistake. In week 3 we have discussed mainly focused on this wastewater characteristics means and its quality parameters. So we have seen what are different wastewater parameters. So if we recap from the first week, in first week we came to know about the what is wastewater, what are its different components, how wastewater is generated. In second lecture, how much wastewater is being generated, we look into that. We did some population forecasting. Based on that population, we did population forecasting because we need to design a treatment plant based on how much wastewater is generated by that population. So once now you have both the knowledge, the third thing which you know, that which kind of wastewater you have to treat. So it's important that we should know about the parameters, like what are different parameters. So during discussion, if you have attended the class, you might have seen the different wastewater parameters such as um, turbidity. The first one is turbidity, then color, then dissolved oxygen, COD, okay, that is chemical oxygen demand, BOD, then different type of solid and all these things. So In this week, first we did some basic discussion about these parameters, and then we some solve some numericals. So and during this session also I will be discussing some basic problem. First we will be going through some theoretical question, and then after some, then at the end of the session there are 4 5 questions which has to be solved numerically. So let's begin with the first question. The first question is related to turbidity. So turbidity in water is usually measured based on. So we have four option, that is measuring rate constant of chemical reaction, gravimetric measurement by weighing, detecting a scattering of light passed through the water, detecting potential for conducting electric current. So before miss, if you have attended the class, this is very simple question, that this scattering, this turbidity is due to a scattering of light. So I will be just recapping the whole thing, how turbidity how turbidity is defined and all. So if you go through the most standard book which is being followed for wastewater treatment is Swear and McCarthy. I will share the uh, book PDF. I will show the which book you have missed. Generally, I have seen at many IIT, at many other laboratory, people use this book only for wastewater characterization. And this so chemistry for environmental engineering and science by Swear and McCarthy. So you can download this book, is available online. You can go to the PDF, through the PDF, and it has discussed each and every parameter in very detailed way. So this is very basic book for to know the different parameter which is related to water and wastewater, such as starting with we have basic concept, basic con- concept for quantitative chemistry, then color, then a standard solution, turbidity, pH, acidity, everything is in this book. So I will suggest to go through this book for more detail. Means I have tried to in, means I have tried to whatever I am writing here, whatever I am presenting here, I have taken from that book, that this book only. So for more detail, you can always go to that book and you can read it for more knowledge. So, turbidity of water is generally defined as a scattering of light by particulate or colloidal matter in water gives water a turbid appearance. Turbid appearance, I hope you understand why what is by turbid means. It's not clean, so there will be some suspended thing. Generally, colloidal particles, which is due to presence of colloidal particles, what will happen that the light which will pass through that system will scatter, and that the a term is related to this phenomena is Tyndall effect. So I won't be going into the Tyndall effect thing, but in simple way, the scattering of light by particulate matter or colloidal matter in water gives a turbid appearance. Turbid water have a aesthetic unappealing quantity and hence unsuitable for drinking purpose. So here I am talking in most common. I'm not categorizing as a wastewater or water. I'm just uh, talking in a generalized way. If you see a water which contains some kind of colloidal particles, that will scatter and that will give a turbid look that it might be of some other color and all. Can you tell me the author? Just 1 minute. Just 1 minute. Can you tell me the author of the book again? Yes, yes. I hope you are able to see my screen. So it's Swear and McCarthy. You can just search chemistry for environmental science, engineering and science by Swear and McCarthy. So this I have taken. Did you get it? I hope you can take a screenshot also. And please note it down. So I think you are doctor. So you are superior than me. You don't need to call me sir. Additionally, turbid water may also contain high concentration of microorganism and suspended solid, which I have already said. So if you look how if there are generally two method of measurement of turbidity, that is, there are two instrument. One is nephrometer and one is turbidity meter, that has been cut. So remember, this instrument is the basic difference is the detector which is kept here. So in if suppose if you have instrument where the detector is placed at, not instrument, if the detector is placed at a 90 degree of path, at a 90 degree in the path of scattering, then that is known as nephrometer. So here you can read, turbidity measurement is based on the comparison of amount of light scattered by sample in defined condition with the amount of light scattered by a standard reference suspension. So this suspension is like there are this instrument generally what contains some kind of a reference, that this reference has this much of turbidity, and depending upon that reference we calculate the turbidity of our sample. The scattered light from the sample can be measured by light placed at right angle to the original path. So here you can see that mm, this is our light path, and the detector which is this is photo tube. Okay, this photo tube is placed at a 90 degree at with respect to the path of light source. This technique is known as nephelometry, and P naught by P will be lower for the sample that is less turbid. So what will happen that here P naught is our standard, uh, uh, mm, is for our standard. So it will be generally and this is for a standard, and the lower the p naught by p, the sample are is less turbid. So generally what is seen that the sample which we take, the reference which we make are normally of very low turbid. So we make sure that if you look in the mechanism, like what is really happening in the nephrometer. So what will happen that most of the light will scattered through the nephrometer, sorry, the standard solution. So obviously that will be less turbid. The more scattering will happen, more turbid it will be. So generally this more this uh, mm, the more scattering will happen, the more turbid the system will be. And similarly for the another case where the this photo tube or detector is placed uh, in the path of light, then that is known as turbidity method. Okay, na. The turbidity can be measured by shining a light through a sample and measuring the degree of light penetration as measured by the light detector placed in the line to the original light path. It is placed. See, both of system will give the measurement of turbidity. There is no question of which one will give best answer. Both will give better result, but people have developed two type of instrument, one by placing at 90 degree and one by placing in the path of systems. So for example, in my lab this instrument is there. In some lab this instrument will be there, so it doesn't matter. So but if someone asks in how many way we can measure turbidity, then you can always mention there are two methods, that is nephelometry, where the detector is placed at a 90 degree to the light path, and one is in the line of light path. So this turbidity is detecting a scattering of light passed through the water. Okay. Coming to the second question, these spectrophotometers are typically used to measure. So this is again related to a simple thing, a simple phenomena. So before going to the what is this spectrophotometer, we should know what is this. Before answering this question, if you see, this question is very simple, that this spectrophotometer used to measure color. So I will be just recapping the whatever you have been taught in your session. So spectrophotometers are primarily used to assess the color of sample by measuring the absorbance. Remember, this absorbance, there is two things in turbidity. B, measure the scattering, means how much light has been scattered. But here we are measuring the absorbance or transmittance of light as a specific wavelength. So what happened that in uh, sorry, pain. So suppose this is our water sample, and suppose generally, if we look in the procedure of this spectrophotometer, suppose this is our chemical, this is our solution, we add some kind of chemical in it, and it give us some of color. Say maybe it might be uh, of any color. So we have one system here, and generally the spectrophotometer is uses light of ultraviolet. Okay now, so we pass ultraviolet rays at this sample. So what will happen, that this sample will absorb some of the light, or we can say transmittance of light. Okay now, so based on this phenomena, we will be plotting one calibration curve, that how much light has been the absorbance. We will be, from the instrument we will be getting the absorbance value for different concentration. So suppose for zero, obviously in your system, suppose there is no suppose if we are measuring for suppose chromium, so for zero concentration there will be no absorbance. Chromium, remember, chromium 6 can be measured by this photometer. Again for some 0. 0.1 milligram per liter there will be some absorbance. Then again for 0.5 there will be some absorbance. Again for 0.5 there will be some absorbance, and again for 1 there will be some absorbance. We will draw this line, we will be getting this calibration curve. And for unknown sample, from this we have the calibration curve of this between absorbance and concentration. From this instrument we can measure the absorbance for any unknown sample, and we can find out the concentration of that sample. So this is how generally it works. So here there are two things, one is colorimetry and one is spectrophotometry. So colorimetry is use of human eye to determine the concentration of colored species. Because colorimetry is based on inception of material with the human eye, a narrow range of electromagnetic with the wavelength of Itna can only be used. Spectrophotometry is the use of instrument to make the same measurement. It extends the range of possible measurement beyond those that can be determined by eye alone. So here I have already said that we use ultraviolet rays. Generally we use ultraviolet rays, but there are I'm not familiar, but there might be another other spectrophotometer where they use some other kind of range. Okay, so a spectrophotometer, an instrument that measures the amount of light absorbed or the intensity of color at the given wavelength. The intensity of the color can be numerically valued by comparing the amount of light prior to the passing through the sample and after passing through the sample. This quantitative measurement of the light are the transmittance and the absorbance. Okay, now so a very famous law which governs miss how this absorbance is related to concentration is given by this law, that is Beer's Lambert law. Okay now, so A is equal to ABC, where capital A is the absorbance, sorry, huh, where capital A is the absorbance, a small a is the molar absorbability, that is generally that is generally constant for I don't remember whether it is constant for particular instrument or not, but here you can see that also known as extinction coefficient, generally it is a constant. C the concentration of the sample, B the path length. Okay now, so what will happen that we will be keeping our sample in a special instrument that is known as cuvette. Generally, it has a length of 1 centimeter. It can vary depending upon the method, which type of method we are using. Okay, na. So what will happen? Suppose we are taking example of chromium. Chromium is measured at 620 nanometer. I don't remember exactly, but at some nano, the instrument is asked to emit a UV rays at this much nanometer, and what will happen that this length will be 1 centimeter, and this coefficient we already know for our instrument, and based on this we can find the concentration, we can find the absorbance, and again we will do the same procedure that we will be plotting the calibration curve, and based on the calibration curve we will be finding the concentration of unknown sample. Okay. So the third question is at 20 degrees Celsius temperature and atmospheric pressure, the saturation dissolved oxygen level in water is approximately 9 milligram per liter, 2 milligram per liter, 0.5 milligram per liter, 0 milligram per liter. So let's discuss what is this dissolved oxygen in water and its significance. Okay. So water quality parameters, that is dissolved oxygen in BOD. Dissolved oxygen. So see, this is Hmm. Dissolved oxygen concentration in surface water is of great importance. Reduction of DO less than 4 results in difficulties and even death for aquatic fish. The normal DO level of healthy surface water is ranging from 8 to 10 milligram per liter, while the in groundwater it might go to 1 to 2 milligram per liter. Low DO value may indicate the organic pollution or the presence of reduced species in the body, resulting in DO depletion of water. So how this DO is significant to our wastewater? So now if you collected a wastewater, so obviously we have seen in the first class that this wastewater will contain some kind of organic matter. So what will happen? That the oxygen which was initially present here will be get consumed by in degradation of organic matter which is present here. So what will happen that this time whatever the dissolved oxygen which was there, so it will get depleted. So and we know that if the depletion, now suppose you threw one untreated wastewater which has initially a DO range of say 8 milligram per liter. So here fish and everything was aquatic life was very nice. So once you threw a wastewater containing high organic matter, so what will happen that it will start consuming the dissolved oxygen, and the dissolved oxygen will decrease from 8 to maybe 3 2 depending upon the amount of organic matter. So once it is below 3, so might cause this might be a threatening situation for aquatic life. So that's why it is said that uh, we have when we are discharging our wastewater to a freshwater body, we have to make sure that all the organic matter which is there uh, is all the organic matter which is there is treated, and there is no organic matter which is being thrown to the freshwater, because um, that will simply decrease our dissolved oxygen, and that may cause will be indication of a pollution. Okay. So we can see that with time, so there is one mathematical expression. I'm not going into that mathematical expression, but remember, suppose we have a gas, we have a water. So at height, what will happen that initially, if we talk about the solubility, so what will happen that we know that there is one Henry law. So with Henry law, so that defined that now concentration in water is directly proportional to uh, is dependent upon the partial pressure of that gas. So due to that effect, there will be some dissolution of dissolution of gases in the water. So at low temperature, what happens that the gas the movement of gas is very slow. So what will happen that it will try to remain in the water, but as temperature increases, so what will happen that the air molecule will get some kind of motion kinetic energy due to rise in temperature, so it will escape the system. So initially at low temperature, so we can see that the dissolution of gas is dissolved oxygen is high at low temperature, but as temperature decreases, so temperature increases, dissolved oxygen decreases. Okay, so the correct answer for this question is 9 milligram per liter. Okay, so coming to the fourth question, DO vary with water temperature and altitude as. So there are four options. So you have to mm, look into the concept of two things, but that how pressure. So only thing which you know should know that the at high temperature the gas have some kind of energy, so it will try to escape from the water, and at altitude as the altitude rises, the pressure decreases. Okay, so we will look into each and every option. The solubility of gases in liquids such as oxygen in water is influenced by both temperature and pressure. Effect of temperature. Inversely relationship. As the temperature of the liquid increases, the solubility of gas decreases. This is because at higher temperature, more energy to higher temperature provide more energy to gas molecules, making them more likely to escape from the liquid into the air. Okay, this I have already explained. In colder water bodies, hmm, in which in colder water bodies you typically find higher dissolved oxygen level compared to the warmer waters, which is why aquatic life can be often be more abundant in colder environment. So, and if we talk about the pressure, there is direct relationship. As the pressure increases, the solubility of gas in the liquid also increases. High pressure pushes the more molecule into the liquid, increasing the concentration of dissolved gases. Okay, so for practical at higher altitude where the atmospheric pressure is low, the dissolved oxygen gas in the water decreases. Conversely, in the deep water or under high atmospheric pressure, the gas solubility increases. So you can see as we go higher, the pressure is low, the gas will not dissolve as much as expected as compared to the gas which get dissolved at higher pressure. Um, this again can be explained with the Henry law only, that partial concentration in the air concentration in the water or solution depends upon the partial pressure of that gas over that system. Okay, higher temperature lower gas solubility, higher pressure higher gas solubility. Okay, so the correct option is C. The cold water holds more oxygen than warm water, and water at lower altitude hold oxygen than the water at higher altitude. So this is due to temperature and this is due to pressure. Okay, I hope this is all clear to you. Hmm. So another question is another question is the pH of water was measured at 6.4 unit. The measured total alkalinity and the measure total acidity of the water would be. So first you should know that what is alkalinity. So alkalinity generally is defined as the certain species to neutralize H plus ions in the water. So ability to neutralize H plus ions is known as alkalinity, and alkalinity is generally caused by OH minus carbonate. This is caustic या hydrocaustic alkalinity या hydroxy alkalinity, carbonate alkalinity and bicarbonate alkalinity. So at 6.4 pH, first you should know that are these three ions present in the system. So this can be, so we know that pH is equal to uh, minus of log of activity of H plus. See, remember I am using activity, so there is some activity and concentration thing. I miss if you are not aware of this activity of thing. Okay, you can just say that minus of log of concentration of H plus. Okay, so and so this pH, as pH is 6.4, then H plus concentration will be H plus concentration will be 10 की power minus 6.4. Minus 6.4, and we know that for H2O, uh, when sorry, H2O dissociates, it give H plus and OH minus, and the Kw, which is defined as equilibrium constant for these two, that is H plus into OH minus, OH minus is 10 की power minus 14. So here, from here you can see that the OH minus concentration will be around how much? It will be 7.6. Okay, 7.6. Total will be, it will be 6.4 and 7.6. Now remember, we have something called log CPH curve. So log CPH curve gives us the at which concentration, at which pH, which species will be dominant. So if we plot the log CPH, this is see, this can be plotted. So again, there is I can refer you some books, so you can go in detail how this has been plotted. But for now, just remember there is log CPH curve which tell us at which pH which species is dominant. Okay, now so you can see that this H2CO3 aqueous, star means aqueous. So now we know that there are two H plus, so it will dissociate at 2.1. Hmm. As it has, so it will dissociate at 2.1 at this point and 1 at this point. Okay, now. So, this value is around 10.35, 10.35, and this is around 6.3, 6.33. Okay, now. So you can see that below this pH, this aqueous H2CO, as this is a weak acid, so not all H2CO3 will be dissociating in H plus and HCO3 to minus. Some will be in the form of H2CO3. So below this pH, this will be dominant. After this, between this and this pH, this bicarbonate will be dominant, and at temperature, at a pH greater than 10.35, this carbonate will be dominant. So here you can see that at pH 6.4, which lie around here, so at this pH, this bicarbonate will be, some bicarbonate will be also there, means bicarbonate will be most dominant, but some carbonate will be also there. So here means, and already we know that OH minus is 7.6. Okay, so all forms of is there, so we can say that yes, there will be alkalinity, so we can say that this alkalinity will be greater than 0. So our answer will be either B or D. So sorry, sorry. This is alkalinity. So either answer will be C or D. Okay. So let's look into what is what is so before going to acidity, I will discuss more thing about alkalinity also. So the experimental alkalinity is determined by titrating a sample with either 0.01 normal HCl or 0.02 H2SO4. Indicator used are phenolphthalein and methyl orange indicator. So methyl phenolphthalein indicator the pH above pink above pH 8.3, colorless below 8.3. Methyl orange indicator is yellow above 4.5 and orange below 4.5. Okay. There is one direct formula also. If you know the concentration of each ions, you can directly find the alkalinity, that is H plus minus H plus plus OH minus plus H2CO3 concentration of bicarbonate plus twice the concentration of carbonate in equivalent per liter. So you have to convert these into equivalent. More direct formula is given as, if you miss, so see, actually not more direct formula. Generally in your question the concentration will be given in terms of mm, milligram per liter, so you can just convert milligram per liter into equivalent weight, and then you generally alkalinity is reported in milligram per liter CaCO3, because it's easy for calculation and we have to compare this alkalinity with the hardness. Okay, so that's why it is also converted, so you can just multiply with the equivalent weight of uh, CaCO3 and you can get the alkalinity of the system. On the other hand, the acidity refers to the property of the acid that can donate H plus to the base. Strength of the acid is often measured by the ability to donate protons, and it typically it is opposite of alkalinity. In simple word, you can say the ability to neutralize OH minus. So as we know that at the 6.4 we have around 7.6 H plus concentration is 10 ki power minus 7.6. Sorry, H plus is already, sorry, H plus, huh? H plus is already 10 ki power minus H plus, and acidity is only caused due to H plus. Okay, na? So H plus is at 10 ki power 6. How much H plus is there? 10 ki power minus 6.4. So obviously the alkaline acidity is greater than 0. So the correct answer is D, that is alkalinity greater than 0 and acidity greater than 0. Okay. Coming to the sixth question, among the given option, the likeliest value of BOD of the wastewater sample having itna milligram COD each. So first know the full form of COD, that is chemical oxygen demand, means how much oxygen is demanding by all the chemical which is present in your water. So generally it is a measure of the total oxygen required for chemically oxidize both organic and inorganic substance in a sample of water. It is determined by using a strong chemical oxidant, typically potassium dichromate, in acidic medium. So we took our sample, we add chromate, and we add some kind of acid to make acidic condition, and in that way we do some experiments. So there is some set of experiment. We use ferrous sulfate, that is ferrous sulfate, to titrate the system, the color, so there will be some color change. Based on that color change we can identify how much FAS is consumed, and there is one set of formula, means there is whole procedure where you can find COD. Okay, now so you can read in that book, the book which I have referred at during the initial time, during the uh, in the first slide. You can always check how the experiment is proceed, how experiment is done. It is determined. COD provide the estimate of total pollution load in the water, including both biodegradable and non-biodegradable substance. A higher COD value indicates the great amount of organic and inorganic pollutant in the water. On the other hand, BOD is the measure of amount of oxygen. Remember the full form of BOD: biochemical. Remember, biochemical oxygen demand. BOD is the measure of amount of oxygen that a microorganism required to decompose organic matter in sample of water over a specified period, usually 5 days at 20 degrees Celsius. So generally, BOD is measured for 5 days at 20 degrees Celsius. Remember this. That's why it is written BOD 5. It indicates the degree of pollution in the water and reflects the amount of biodegradable organic matter present. At higher BOD value means a higher level of pollution, as more oxygen is needed by microorganisms to break down the organic material. In summary, BOD measures all the oxygen demand of biodegradable material in the water. COD measures the total oxygen demand, including both biodegradable and non-biodegradable materials. BOD is generally a fraction of COD. So remember this only measure biodegradable, and COD always measures BOD plus biodegradable plus non-biodegradable. So obviously BOD will be less than COD. Sometimes it can be equal to COD also, but that is very rare case. Generally it is that is real case, but So here some rare case. So the BOD generally affects on COD. In most cases, BOD is significantly lower than COD because COD measures the total amount of oxygen required to oxidize both biodegradable and non-biodegradable substances, while the BOD measures only the oxygen demand by biodegradable matter. So obviously, in this question, at COD is 450, then option less than this will be, and obviously BOD if it is not that situation also that. As it is saying that it is a wastewater, so there will be some organic content. So the answer will be this 270. So someone can mark this 450 also, but this is very rare case that COD is equal to BOD. If suppose COD is equal to BOD in only that case where there is no non inorganic or non biodegradable material, but in wastewater there will be both biodegradable and non biodegradable. Okay. Uh, Coming to the question number 7, match the type of effects of improper wastewater management. So this is a question similar to this question is similar to the question asked in uh, this is a question similar to the question asked in lecture 1. Hmm. So what if the there is improper wastewater management? So what will happen then? Inorganic first in what will inorganic pollutant organic pollutant will cause? Organic pollutant will give BOD and COD. Okay. Emerging contaminants. What is emerging contaminants? They are newly and recently recognized pollutants that are not commonly monitored or regulated but have significant environmental and health impacts. Example: antibiotic, pesticide, PFAS. Currently emerging pollutant is there, contaminants is there. Then this will be due to antibiotics and pesticides. Then we have other option nutrition. So already said that this is nutrients as phosphate and nitrogen and phosphorus is major constituent of nutrients. So this orthophosphate and nitrates will be going to this nitrates option. So organic pollutant they refer to substances that are primarily carbon based and can be measured by parameter like BOD, that is biochemical oxygen demand, COD chemical oxygen demand. These are indicative of amount of organic matter in the wastewater. Yes. Similarly for emerging contaminants and nutrients, these are the substances that can lead to eutrophication in water bodies. Okay now. So remember I have already discussed in lecture 1 that if a water receives high amount of nitrogen and phosphorus, that lake can convert that that will result in alga growth. Alga growth because algae, the source of food for algae is this nitrogen and phosphorus. So this will this process is termed as eutrophication. Matching this category, we can say that 1A, 2C, 3B. That is organic pollutant is related to BOD and COD. Emerging contaminated are antibiotics and pesticides. Nutrients are orthophosphate and nitrates. Okay. So question number 8, the BOD5 of two wastewater A and B are measured at 80 milligram per liter and 220 milligram per liter, 210 milligram. This signifies that. So remember, what did I say? This more the organic compound, more oxygen will be required. That means more biochemical oxygen demand will be biochemical oxygen demand will be there. So a BOD5, that is biochemical oxygen demands over 5 days, measure the amount of oxygen consumed by microorganisms to decompose organic matter in wastewater. Higher BOD5 value indicates a higher load of biodegradable organic matter. Given the BOD5 value, sample A this much, sample B itna, sample B has higher BOD value. This signifies that A that it has a greater amount of biodegradable organic matter compared to the sample A. Therefore, the correct option is sample A has a lesser biodegradable organic matter load than sample B. I hope this is very clear to you. Identify the incorrect statement regarding emerging contaminants or the contaminants of emerging concern. Statement 1 is emerging contaminants are generally bioaccumulative but are non-persistent and have very less toxicity. So remember, all the contaminants which is there are more or likely are toxic in nature. So first statement is incorrect. Without knowing what is this bioaccumulative, what is this emerging contaminant, you can answer this that this is wrong statement. Emerging contaminants have become relatively easily identifiable with the new techniques for the chemical identification and separation. So this also without any prior knowledge, you can say obviously with the advanced technology which we are working right now, we can right now detect anything present in our system, any kind of unknown contaminant we can just measure. So the emerging contaminants, also known as contamination of emerging concern, are the substances that are increasingly being recognized as a potential environmental and health hazardous. So obviously these are health hazardous, but are not widely regulated through study. These contaminants include pharmaceutical and personal care products such as antibiotics, hormones, and cosmetics. Then endocrine disruptors, chemicals that interfere with the hormonal system, including some pesticide and industrial chemicals. Nanomaterial, engineered nanoparticles used in various applications that might have unknown effect on the health and the environment. Industrial chemicals, substances used in manufacturing or processing that might be persistent and bioaccumulative. Okay, so bioaccumulative means with so here is the definition of bioaccumulative. Bioaccumulative, they can build up in organism over time. So what will happen that generally when we eat our food, uh, we store some kind of. What will happen that it will keep storing in our body at in a very less, very small amount. At after some time, it will be very toxic to us and very hazardous to us, and it might even kill. Okay, they can build up in organism over time. Persistent, they may not likely break down in the environment. Toxic, they can be harmful to the health or ecosystem, though their exact effect may not be always be understood. Emerging contaminants are often identified through advancement in analytical techniques and research, revealing their presence in environmental media. So there are several techniques right now. One of the they commonly use is one ICPMS is there, where we measure different type of elemental concentration, or it's for measuring organic things. We have also some kind of instrument. So we have very advanced techniques. So statement one was emerging contaminants are generally bioaccumulating but are non-persistent and have very little toxicity. Emerging contaminants are often characterized by their bioaccumulative nature and potential toxicity, but they are not typically persistent. In fact, many emerging contaminants can be persistent in nature, meaning they do not break down in obviously I have already said that this one is incorrect. A statement two is emerging contaminants have become relatively easily identifiable with new techniques for chemical identification and separation. So advances in analytical techniques have indeed improved the ability to detect and identify emerging contaminants. So we have more advanced techniques. The technology such as high resolution mass so high resolution mass spectrophotometry and advanced chromatography method have made it easier to identify the both. So these are some of the techniques where researcher uses to identify the contaminants. So based on this analysis, a statement two is correct. A statement one is incorrect. Okay. So one numerical question now. I think we have numerical question only. Hmm. A wastewater contains this much milligram per liter of acetic acid, CH3 3 will be in subscript. The contribution of acetic acid to the theoretical COD of the wastewater is governing oxidation equation. So you have to say how much COD is there. So from this equation you can see that this 1 mole of CH3 COOH is consuming 2 mole of oxygen. Okay, so 1 mole of acetic acid is oxidized by 2 mole of COD, and we know that number of mole is given by given weight by molar mass. So number of mole of acetic acid will be 180 milligram per liter, and the molecular weight of acetic acid is 60. So it will be 3 millimole per liter. Remember, millimole per liter, and millimole per liter is also this. Remember, mole per liter is another mole per liter is another is we call it as a molarity, that is chemical name, molarity, and again it is as it is milli, so that's why it is millimole. So number of oxygen will be moles of oxygen will be as 2 moles of oxygen are required for each mole of acetic acid. So the moles of oxygen will be 3 into 2, that is 6 millimolar, and the mass of oxygen will be 6 into 32, that is 192 milligram per liter. The theoretical COD of theoretical COD will be 180 milligram acetic acid will be 192 milligram per liter. So to consume this much of acetic acid, this much of oxygen is also required. So if that water has this much of oxygen, then this much of acetic acid can be completely consumed. Okay, so this was very easy question. You can expect this type of question in exam. Now this is important thing, that this is complete BOD thing. Okay, now so 5 ml of wastewater sample was diluted with aerated distilled water made up to 300 ml in BOD bottle. The initial DO was measured as 8.2 milligram per liter, which dropped to 1.8 milligram per liter in 5 days time. BOD 5 of the sample. So before solving this question, I will be going into the details what is how this is solved, how this experiment was done, how this initial BOD, final BOD, and why 300 ml. Okay, na, so there must be curiosity, why 300 ml, why 5 ml, 5 ml was sample, but why 300 ml BOD bottle and all this thing. Okay, so I will be going one by one. So BOD, which is termed as biochemical oxygen demand, oxygen required for decomposition of biodegradable organic matter, that we have already seen. It is a wastewater parameter. Remember, someone might ask you what is the BOD of drinking water. So BOD of drinking water is not defined. BOD is only a parameter for wastewater, not for drinking water. So this is general question in many interview. Define what is the critical limit of BOD in drinking water. No. If there is BOD, biochemical oxygen demand, means there is some organic content, means that water is polluted. You cannot drink that water. So that's why BOD is not defined. Remember, you cannot say zero. It's simply not defined. Can we say zero? I have to check. Hmm. Remember, this is for wastewater, means for drinking water. BOD is not defined only. Okay, now some we cannot say zero if something is not defined for something. So I think zero cannot be just simply say that BOD is wastewater parameter, not a drinking water parameter. Determination of involves a measurement of dissolved oxygen by macroorganism in the biochemical oxidation of organic matter. So we cannot measure directly BOD. We have to measure dissolved oxygen. Okay, now the biochemical oxidation is slow process and theoretically takes time, infinity time to go to the completion. Within 20 days period, the oxidation is about 95 to 95% complete, and in 5 days period used for BOD test, oxidation is 60 to 70% complete. So whatever oxidation is going to happen will happen. It will take infinity time for oxidation, but researcher has find out that within 5 days 60 to 70% decomposition has occurred, and within by 20 days around 95 to 99% of oxidation has occurred. So DO is generally determined by azide modification. method. Okay, so this is a method. So the normal DO of healthy water surface remain as 8 milligram per liter. As DO decreases, we can say that water is polluted. Okay, so BOD bottle in this experiment which has a fixed volume of 300 ml. So this experiment is always performed in a BOD bottle. So that's why 300 ml was done, because this has a volume of 300 only. During experiment, sample is diluted as per chemical oxygen demand value. So what happened that if so there is one table in this book, okay na, that defined that this, if this much oxygen demand is there, just let me check, that if this much is your COD, then you have to dilute this much, because we know that DO of the system is around 8 milligram, between 0 to 8 milligram per liter only. Okay, na, but your BOD and COD can be in the range of 500, 400. So obviously you have to dilute your system. Okay, na. So you have to dilute in such a way that you are able to find a proper. So I think this is the table using percentage mix. Uh, I'm not. Let me just check that how much dilution should be done, um, depending upon the COD value. Chemical. It's not written here. I might have forget where I was seeing that table. Okay, now is this that table? Hmm. See, this is if you suppose now you have done your COD experiment, and now you come out to that, you come to know that your COD is maybe suppose 400. So obviously your BOD will be less than 400. So obviously this, you have to select from here that as it will be below 400, so you have to dilute in a such a way that it means it is below 400 only. So you can see here it will, you can select, here it is 300 to 1000. So this dilution will be very large dilution. So again this is 60 to 200, 120 to 420. So we can dilute, we can use this value. Okay, that is 5. We can take 5 ml of sample and we can dilute it to 300 ml. So here you can say, so generally this table is used. Okay, I hope you are getting it. The dilution factor is total volume by volume of the sample. Means total volume is always 300 ml. Volume of the sample, depending upon the volume of sample, you can identify. The initial DO is measured by agile modification method. For 5 days, sample is incubated. So this agile modification method is there, where we use some kind of agile chemical, then we titrate it, and depending upon the color change, we note down our dissolved oxygen value and all these things. Okay? Along with sample, a DO of blank sample will be also measured. So what happened that for dilution you have used water. What if that water is already polluted with some kind of organic matter? So we don't, obviously that water won't be, but we don't want to take any risk. Okay, na. So whatever the reading will be coming for our sample, we will be subtracting that DO for our blank also. Blank sample is water used for dilution, sometimes referred as dilution water. After 5 days of experiment, you have the following data experiment. Initial DO of the sample that you have done initially. After 5 day incubation, you have done this DO5. Then initial DO of the blank and initial DO of the water, sorry, D of the blank after 5 days. Then dilution factor we have DF. Then BOD will be given as DO initial minus DO5 minus DO initial of blank, DO initial of final into dilution factor. So for our question, the DO initial was 8.2 milligram per liter, DO5 was 1.8 milligram per liter, D as blank was not given, so we can take it as 0. Dilution factor is 300 by 5, that is 60. We will be putting the value here. The BOD will be 384 milligram per liter as oxygen. Remember, as oxygen, because we are converting each and everything into oxygen. Okay, so remember this unit, that BOD is in terms of oxygen. So before going to the next question, I will be discussing about this microbiological concept. Okay, so the next question is related to MPN, so that is somehow related to microbiology only. So I will be discussing that thing. Hmm. So microbiology is known as the study of microscopic organism, that is bacteria, viruses, archaea, algae, fungi, and protozoa. Okay, now. So pathogens, microorganism that causes disease in human beings. We know that. So one of the major tasks in environmental engineering is to ensure that water used for human consumption is free from waterborne pathogens. So now in case of wastewater, you know that if you now in wastewater treatment, you have to make sure that there is, after treatment, there is no microorganism. Now suppose what happened that initially the wastewater which was given to you might contain some kind of microorganism. You dispose it without untreated, without treating that microorganism. So what will, just 1 minute. I think you have joined right now, Vishnu. Actually, there was some net problem, so that's why I was not. Uh, Vishnu, are you able to see my screen? Am I audible to you, Vishnu? Just write in chat box. Yes, sir. Okay. So till now, in 1 hour session, I was discussing about some of the basic concept about turbidity, then dissolve oxygen. Then we have solved two questions related to question related to COD and one question related to BOD. So if you have some kind of a specific doubt, you can ask right now. I will try to solve it. Yeah, try to help you. Yeah, I can continue. So I was going through. So next question is related to MPN. Uh, Related to MPN. So before going to what is this MPN, I will be giving some brief discussion about this MPN. So you have any kind of doubt, any kind of question, you can just write down in chat box, or I can continue with this microbiological concept. Okay, so I will continue with microbiological concept. So remember, so microbiology is the study of microscopic organisms such as bacteria, viruses, archaea, algae, fungi, and protozoa. So out of these, some there are some microorganisms that can cause disease in human beings. So that is related to pathogens. That is termed as pathogens. So one of the major tasks in environmental engineering is to ensure that water used for human consumption is free from waterborne pathogens. Okay, now. So when this is about drinking water, like whatever water which we are drinking should be free from any kind of diseases, yeah, waterborne pathogens, because that will cause us will cause disease in us. So if we talk in the respect of wastewater, so when we are treating our wastewater, we should make sure that the we are treating every kind of pathogens. Also we want to kill all the pathogens which is there in the wastewater, so that that can be discharged, or that can be treated in a such a way that it can be used for drinking purpose. So first the task is, first we have to measure that is there any pathogens present in our system or not. So that's why this is a major task, to ensure that water or wastewater is not used for, but you can add one sentence also that treated wastewater used for discharge is free from any pathogens. Okay, you don't want to add any kind of pathogens in your fresh water when we are discharging treated wastewater. The main source of waterborne pathogens is human and animal excreta. Okay, now so this we have discussed in first lecture, that human excreta are major uh, bill, sir. Just yes, there are some miss. There are some. Yeah, I have already discussed 10 question. Yes, I have already discussed 10 question. So this initially I was discussing about this question number 10 about BOD. So actually, before going directly into the question, I just want to give a brief discussion about what how why we are measuring this MPN. So the next question is question number 11 is related to MPN. Then we have question number 11, 13, 14 related to solid measurements in wastewater. So there are numerical problem. This session is specifically for problem solving only. So that's why, if you have attended, I think you have, I don't know if you have attended my last session or not. Last session I told you that I have some question, I will solve it. If you have some question, just try to write in chat box. I will help in solving those questions. If I am miss, I will try, miss, not 100% sure that I will solve it, but I will try to help you. The consumption of water contaminated with human or animal excreta thus may cause waterborne diseases. How to ensure that water for human consumption is free from pathogen is a very difficult task. So water may contain many different kind of pathogen. Water sample must be tested for presence of each of which is typical. So now we know that the water which we have might contain many pathogens, and there are thousands of pathogens in the system. So we cannot measure each and every contaminant which is present in there. There a recorded video of problem, sir? Yeah, this session will be miss. Yeah, the question which I have discussed till now will be uploaded on YouTube channel. So, and YouTube link has been shared to you via mail. You must be getting mails from the recording session of all. Am I correct? You must be receiving. Let me show you which kind of mail you might be receiving. And or I will share the link. You can just tomorrow you can just go and have a look, like what I was discussing. So the recording of this session will be uploaded on this YouTube channel. Okay, so all the session. So and I think you might have received this mail also. I don't know, but this kind of mail you might be receiving, that where the for we here you can, I don't know. Here you can see each and every recording of all the three TA where they are solving the. Uh, just log in to your account, and you will be you will able to get the access of all the recording session. Yeah, problem solving session, July 24. Problem solving recording session. Hmm. Click here to view the problem solving lectures. Here you can see that people have uh, already they have done this thing to for the last 2 weeks they have uploaded it here. This is for my session. These are for other two TAs. So you can always go and check it. So I was saying that we have so many contaminants in our water. We cannot go and check each and every parameter. So researchers have developed one thing, that if that one of the parameter, they just focus on one thing. They called it as an indicator organism. So if that organism is present in your system, then we say that pathogens are also present. So 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 we the indicator organism is coliform bacteria. So what researchers has done, that if this is present in your water, then we can say that your system also contains some pathogens also. Like pathogens, coliform bacteria are present in the feces of all. So the origin of this bacteria is from the feces of all warm blooded animals and humans. The number of coliform bacteria present in the feces is in order of magnitude higher than the pathogenic bacteria. However, the coliform bacteria are themselves generally not pathogenic. Remember, these are not pathogenic. However, their presence in drinking water indicate the pathogens could be present. Remember, could be present. This is not also sure for sure that if this is present, but a method has been developed just to say that yes, if this is present, then pathogens are also present. It is relatively easy and expensive to test for coliform bacteria. So, if coliform bacteria are found in a water sample, the water may contain pathogens and hence is unlikely for unsafe for drinking without disinfection. Similarly, if we are talking about wastewater, then it is unsafe for throw that if a wastewater is being treated and if contain this much of. So remember, depending before treatment also we measure this thing. If obviously pathogens will be present here, and after treatment also we measure this we do some test to measure the indicator pathogens also. The water may contain pathogens and hence is likely for unsafe for drinking without disinfection. Water not containing coliform bacteria is unlikely to contain pathogens. So water not containing, if coliform bacteria is not present, then we can say that it unlikely to contain some pathogens. So there are two things: total coliform and fecal coliform. Total coliform is all kind of coliform that is present in water, and fecal coliform are only those coliform which are coming from the feces of humans and animals. Okay, now. So total coliform, fecal coliform, and E. coli are the indicator of drinking water quality. The total coliform group is a large collection of different kind of coliform bacteria. Fecal coliform are type of total coliform that mostly exist in feces. Okay. The E. coli is a subgroup of fecal coliform. One strain of E. coli is pathogenic. Presence of E. coli in water sample indicates recent fecal contamination. So these are different kind of coliform which you should know that. But for our water we only measure total coliform and fecal coliform. Okay, now so there are different procedure that when to how to do total coliform test and how to do fecal coliform test. So testing for coliform bacteria, so there are some technique, so I will be just going in brief. If you are a btech student, you will be doing this experiment in your third year course, maybe in fifth semester or sixth semester. Generally in fifth semester, they are this type of test is being asked to do. Yeah, often the bacteria contamination is, so remember, um, testing, there is some technique, because we know that this this water sample may contain high amount of bacteria, and suppose if we are doing some kind of experiment, then chances are that that we might be getting unsatisfactory result, yeah, over predicting result. So we have to dilute our system, and upon dilution we will be again multiplying by dilution factor and all this thing to get the proper result, but that is another thing. But the technique which is used is serial dilution technique. Often the bacterial contamination of water is high enough to require dilution before enumeration by standard techniques. Water samples are diluted by serial dilution technique, which is illustrated in following figures. So now what will happen, that this will be our original sample, which contains high amount of, which might contain, I'm not saying which will contain, which might contain high amount of bacteria. So now what happened, that I will be taking 1 ml of sample from here, and I will be adding in another beaker. And now suppose it has a total volume of 9 ml, okay na, sorry, 10 ml. So what will happen, that I will be taking this will be completely 10 ml of our sample. From this sample I will be taking 1 ml of water, 1 ml of sample, and I will be adding 9 ml of pure water or ultra pure water. The first tube contains 10 ml of the undiluted sample, means original sample. The 1 of ml of this sample is transferred to the second tube, which already contain 9 ml of sterilized water, which has already contain 9 ml. This procedure is followed to obtain larger dilution. So we can now suppose again, suppose um, this is just systematic, that we can do dilution up to 10 ki power time, 10 ki power 5 times, but this can go even more, okay na. So this type of dilution is done, okay. So now what will happen, that what we have to check, we define one term, that is most probable number, that what is the probability that this sample contains some kind of a indicator bacteria. So what happened, that suppose if we have taken water from here, so there are high chances that the pathogens which were present in there is not being collected, or there are these chances also that are you but there are again this chance, there are two cases. The pathogens might be present in the sample, and pathogens might not be present in the samples. So we have to check a probability. So here we are not going to the direct numbers and all, we will be just checking the probability, that what is the probability that I have collected a pathogens and all this thing, okay now. So you will, when we will look the formula, we will go. So a most probable number theory is given, where it is said that let n be the number of organism in the sample of volume v. Now suppose our volume was how much, 10 ml, okay. So and the number of samples in that organism is n. Therefore, the average number of organism per sample is n by v. Okay, so there are n organisms. So miss how many organism per ml is there? N by v. Obviously, suppose there are 100 samples, 100 organism in 100 ml. So on per ml will be one organism. So this is just a probability that there are high chances that in 1 ml a high number of pathogens might be there, but we are just defining a probable number, okay. Let note that this doesn't mean that every 1 ml of allocate will from this original v sample must contain lambda organism. Remember, this is what I said, that if 100 ml of sample contain 100 ml of organism, then it doesn't mean that every 1 ml of sample will contain one organism, okay na. So in fact, any particular 1 ml liquid may have 0, 1, 2, 3, or n organism. The probability that one, so now the question is, what is the probability that 1 ml which I have taken from that sample will contain this much of bacteria? Means how many bacteria will that sample contain? The probability of that is given by this equation. This is px lambda x exponential of minus lambda by divided by, this is uh, uh, Poisson distribution, I think. Poisson distribution, just check it. Thus, the probability of any 1 ml of sample with no organism. Suppose this x is 0, then probability that there is the 1 ml which we have taken does not contain is given by px, that is e minus lambda. X will be 0, then this will be 1, this will be 1, then e minus lambda. And the probability that 1 ml of sample having one or more organism will be 1 minus one minus probability that no organism is there. So this is a this is how this ambient theory is defined. So there are different method to solve it. So summary of the so what happened that uh, how this experiment is performed. So once you have done dilution of each and every sample. You have done dilution, so we prepare one broth. This is fermentation media. So what will happen, this fermentation is that now suppose if um, this this tube, yeah, this sample. I can discuss, miss, I will just okay, I will after this after completion of this thing, I will just go into those some few problems. uh, yeah, I can do that. Just let me finish this thing, okay now. So sometimes, just in short, I'm saying that this there is some organism is there. So it if I provide some food to it, so what will happen that this will consume that food, or that will ferment that food, and a gas will release. So we will collect that gas. If for any sample, the if gas is being generated, then we say that this is a positive this is a positive experiment, means positive tube, and there might be some bacteria, there will be some coliform in that bacteria. So this, remember, this little tube is known as Durham tube, and this is used to collect gases which will be produced after fermentation, okay now. So remember this, see, the gas has been collected in this Durham tube, okay. So 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 uh, now suppose if I perform experiment with this much dilution, that original sample was taken, 110 time dilution was done, 100 time dilution was done. So what will happen that after experiment you find out that all for all original sample, the gas was collected for 1 is to 10, 1 is to 10 time dilution, that for 10 time dilution only one tube was giving positive result, and for 100 time dilution no tube was giving any kind of result. So so we know that to calculate the ambient value, we know that this p lambda will be given. How we have defined this p lambda? P lambda will be either e minus lambda or 1 minus e minus lambda. Here no no pathogens are there, here some pathogens are there, okay now. So so if for first case, all three are giving some kind of pathogens. So the probability will be 1 minus e ki power minus lambda, as three tubes are there, so this probability has been multiplied. Similarly, here only one is giving positive results, that is why 1 minus e minus lambda, and the volume has been multiplied. And for two negative case, e minus 0.01 lambda. And similarly for this 100 time dilution, a simple e minus 0.00 0.01 lambda की power 3. Okay na. So to find the most probable number, that is maximum value, we can just differentiate it. The MPL value for the define as the lambda for which the value p lambda is maximum. The solution can be obtained analytically or by plotting the value of p lambda versus time using a spreadsheet software and observing the value of lambda corresponding to the maximum value of p lambda. So one is that we will be doing p lambda by p, p lambda by d, derivative of this, keeping it as 0, but that will be a very difficult task because integrating this will be very challenging. Not challenging, but you can differentiate, but it will be little bit challenging. So what we do is that we can use some software to plot the graph. So if you plot this graph, it will come out to be like this. Okay na. So wherever this is maximum, that will be your lambda and that will be your MPN value. Okay. Another method is use of Thomas formula. Thomas formula is simple: number of positive tubes into 100 divided by under root ml of negative tubes into ml of sample in all tubes. So for example, for here the suppose if 10 ml sample is there, here 10 ml sample, here 10 times dilution is there, means 0.1 ml sample is 1 ml sample is there, and here 100 times dilution is done, means 0.01 ml sample is there. So number of positive ml is 10 plus 10 plus 10, and this is 1, means 31. So here it will be number of positives is 4 into 100 plus ml of negative, you can just substitute. So I am just giving you one example, that a sample size of 10 ml, 1 ml, 0 point, and experiment was done where sample A, sample B, and sample C was done. Sample A and 3 tube was selected. Okay now, 3 tube was selected. Uh, so here you can see that for sample A, 3 tube was selected, and out of which 2 was positive, 1 was negative, and for 1 ml 1 was positive, 2 was negative, and for 0.1 2 was positive, 1 was negative. So this will be your Poisson distribution equation that can be simplified into this. So either I can solve it dp lambda, I can do dp lambda by this thing, or I can plot the graph between p lambda and lambda, and here you can see that at this location this is maximum. So from graph we can say that lambda is 0.0 per ml, so per 100 ml it will be 27. Another method was another another method is this positive tube method. Okay na. So here you can number of positive tube is 5, then negative sample is 2 point, I can substitute fellow. And another method is use of MPN table. Okay na. So there miss scientific have researcher has developed one table uh, where people can use that uh, just I'm showing that table. So as we were using three tubes. Okay na. And here we can see that uh, um, three tubes, and here we can see that two are positive, means the code will be 2 1 2. So from here you can see that 2 1 2 and here it is 0.27. So 0.27, that is per ml. Okay na. So mpn per ml, and we have to similar result was obtained from this graph also. Okay na. So you can just say that uh, either use that or this table on there is Thomas formula, means there is some calculation mistake here, it should not be 249, it will be around 27 only. So I will recheck it why this is wrong. Okay na. So I hope you have got it what I was saying. Huh. So the question number 12 for this session is that in MPN test 10 ml 1 ml and 0.1 ml wastewater was inoculated in 5 replica in nutrients broth, resulted in 520 positive, means out of for 10 ml 5 were positive, in 1 ml 1 2 was positive and 0.1 0 was positive after 48 hours of incubation. The MPN index per 100 ml of wastewater would be, and so they are asking you to use, so on internet you can find these tables, okay na. So just similarly, if you have done for 3 tube, you can use three tube, three tube table. For this question we have used five tube, so we will be using 5 tube table. So here what was our code? Our code was 520. So here you can see 520 520 520 520 here 531 520, and the MPN is 49. 49, you just always check for the unit. If nothing is written, it will be MPN per ml. Okay, MPN per 100 ml. Okay, so here you can see the answer is MPN per 100 ml is 49. So the answer will be 100 ml, MPN per 100 ml. Okay now. So this was question related to MPN. Prior to that question, I have solved one BOD question. Okay, so just I, uh, I am recapping the first question which was discussed prior to discussing to this question was this. Uh, hmm. So the first question was that a wastewater contains this much of acetic acid. The contribution of acetic acid to theoretical COD, given that this is the oxidation reaction. Okay na. So here you can see just simple stoichiometry was supposed to be done, that we can from this equation we can see that 1 mole of acetate is consuming 2 mole of oxygen, and we know that number of moles is given by given weight by molar mass of that element, yes, compound. So here acetic acid is given, so given weight is 100 milligram per liter, 100, and molar mass of acetic acid will be CH3 12 plus 3 plus 12 plus 32 plus 1. If you add up, it will come out to be 60. Okay now, so 180 divided by 60 is giving us this gram and gram will cancel out, this mole will be millimole per liter, and we know that mole per liter या mole per liter has another unit. Mole per liter has another, is also known as molarity. Okay na, so that's why we have written 3 millimole. Okay, so number of oxygen will be so the acetic acid mole is 3 mole, and we know that for 1 mole 2 mole of oxygen is required, so mole of oxygen will be 3 into 2, that is 6 millimole. Okay, so and we can again we know the mole, then here again by using this formula we can find out how much oxygen in gram will be needed. So 6 into 32, because oxygen molecular weight of oxygen is
Sir, what is milligram, sir?
uh,
What is mg per ml, sir?
m2
Mg per ml, sir.
mg milligram per liter. We know kg.
Okay, okay, sir.
No kg na, kg is 1 kg means 100 gram.
Okay,
Sorry,
sir.
1000 gram, 1000 gram.
Okay, sir.
And again this another unit of weight is milligram, that is uh, uh, this 1 kg barabar 1000 gram. Okay, and similarly 1 gram is, you might have meter, centimeter, decimeter, millimeter. Similarly gram, kg, gram, milligram, and 1 gram is 100 milliliter, 100 milligram. Got it?
Okay, sir.
Okay, so it is just saying that if you take 1 ml of 1 liter of sample, in that 1 liter 180 milligram of acetic acid is present. Miss, just a simple, you can visual, like suppose if saying that this water contain 100 gram of iron, 100 gram of iron, so you can just imagine that if I take 100 1 liter of that water, then in that water I can get 100 milligram of iron. It's it's a unit of concentration. Generally we define concentration in these terms, okay now. So one term is this mole. Also mole is also a representation of concentration only, that how much mole of that particular element is in that water. Did you get it?
Sir, how to calculate the mass of oxygen, sir?
Mass of oxygen, the atomic, oxygen is O2. Oxygen is O2. So, what is the atomic number of what is the atomic mass of O? It is 16. Atomic mass of O2 is 16, na? And as there are two atoms of oxygen in oxygen, so 16 into 2 will be 32. Did you get it?
Okay, sir.
Here is the C. If we are, how will we? How you tell me now? How I have got this 60? Here I have molar mass of acetic acid. I have written a 60. So how I have calculated this 60? The formula is written here. You can take help of this formula. So to calculate the molar mass, how what we do, the what is the procedure to calculate the molar mass? We multiply the uh, uh, atomic mass, yeah, molar mass of that element, that element into how many. Sorry, we first identify how many numbers of atoms are there in that. Hello.
Hello?
Yes, are you
Yes, sir.
following? Huh. So how many carbon is there in my formula? How many carbons are there? One carbon and two carbon. Two carbons are there.
Two carbons.
How many hydrogen are there?
Two.
No, hydrogen actually three. Just focus on this formula. This formula. This, forget it should be subscript. So how many hydrogen is there? Three hydrogen here. One hydrogen here. So total how many hydrogen? Four hydrogen. And how many oxygen are there?
Two oxygens.
Two oxygen. Two oxygen. Which one? This much and this one. Two oxygen is there. Okay. So now you know each and every element in your system. Now what is the molar? What is the molar mass of carbon?
It's
No, it is 12.
wait.
12. Molar mass is 12. Carbon. Are you getting? Did you miss? You can check periodic table. What is the molar mass of different elements? What
Okay,
is
sir.
the molar mass of hydrogen? It is 1. And similarly, what is the molar mass of oxygen? It is 16. Okay, so you have to, this was molar mass of single element. Okay na, so uh, how many carbon atom was there in system? Two carbon, so it will be the complete molar mass will be 12 into 12 into 2, 12 into 2 plus 1 into 4, 1 into 4 plus 2 into
Okay, sir, I understood.
2 into 16. So if you add up all things, you will be getting as 60. Yes, this is you should remember the molar mass of basic atoms like carbon, hydrogen, oxygen, nitrogen. So you have to follow this procedure only. So can you tell me what will be the molar mass of CO2?
C2. 64, sir.
How have you calculated 64?
O2 molar mass 32, sir.
O2 molar mass, okay, O2 molar mass means 32. O2 molar mass 32, and then
32 to the 64, sir.
no, actually CO2. I am just asking of CO2.
CO2.
CO2. CO2. How many carbon atoms are there in
One
CO2?
carbon.
One carbon atom. How many oxygen atoms are there?
2.
So, and what is the atomic mass of carbon?
12, sir.
And what is the atomic mass of oxygen?
16.
Will be multiplying 1 into 12 plus 2 into 16. So what it will be total? 1 into 12 plus 2 into 16. How much it will be?
34, sir.
44 na?
44.
44, 44.
Okay. Okay, sir.
Got it?
Okay, sir.
Now last, calculate for H2O, this H2O. H2O, this H2O. Did you get it?
Yes, sir, I get, sir.
How much? How much it will be? Just use the concept which I have told you. How many atoms of hydrogen is there and how many atoms of oxygen is there? How many atom of hydrogen is there? Hello. Vishnu,
Hello, sir.
what will be the molar mass of this H2O?
So,
So how many mole of hydrogen is there in this system? Hello, it is 2, and how many oxygen is there? One oxygen is there. And we know the atomic mass of hydrogen is how much is atomic mass of hydrogen?
2 into 1.
2 into 1, and for oxygen it will be 1 into
16
1 into 16. So total it will be 18.
to 24.
18 na 16 plus 2 18.
Okay, okay.
Where you are miss, where you are facing problem, just tell me. I will just try to give another example. Should I give
Okay,
another
sir, I
example?
get.
Should I give another example?
No, no. Next problem.
This is sodium Na2CO3. Find the molar mass of this sodium. Sodium molecular atomic mass is 32. Sorry, 23. 23, not 32. 23. This is 23. Sodium atomic. Hello. Just find the molar mass of this Na2CO3. Hello, are you there, Vishnu? Hello. Last three question. Hello, are you there? So please respond.
Sir, 96, sir. In A to CO3.
Na2CO3 90.
96.
96. Yes, 96 it will be. Just recheck it. How have you done it? Na2CO3.
Sodium 23, sir.
23.
23 into 2, sir.
हाँ.
Na2.
See how much. That is good. That is correct. 23 into 2. Then
Uh, plus carbon 1, sir.
carbon 1. Carbon not 1. Carbon 12.
12.
हाँ. Hydrogen is 1.
Okay, sir.
Carbon 12. Then
Oxygen 16.
oxygen 16 into how much?
16 into 3, sir.
To 3. So total will be how much? Use calculator.
106, sir.
106. 106 is the correct answer. So I will request you to go look at the periodic table and try to memorize the atomic mass of each and every element.
Okay, okay.
Because this is some basic question and you should know about this thing.
Okay, sir.
Okay, now so I think I won't be discussing any further question. So just in the for the next lecture, just you miss try to memorize the most atomic mass of the most common elements, because that will be very useful, because this question you should be able to, you don't have to take this much time. You should be able to do, you should be doing these calculation very fast, in a very rigorous way and in very fast way.
Okay, sir.
Practice more and just go through the recordings which I have which will be posted soon, and join in the next session. With if you have some more doubts we can discuss. As you can see that for my session the number of students are very less, so we can have one to one interaction in a good way. So I will be happy to help you.
Okay, sir.
Okay, so I will request you to join please join next session. And you don't we don't have to go to the whatever is being whatever the question which is there here to discuss. If you have some particular question through some for some concept, then I can discuss that thing also, given that the number of students which are joining is very less. And okay now. Okay, so that's all for today.
Sir,
Yeah.
one question remaining, sir.
One question. This question is for like. One question is remaining. This question is like 100 ml of wastewater was filtered using a filter paper that weigh this much gram. So what you did that you took one filter paper, you weigh it with a weighing machine, and it came out to be 1.750. And the filtrate collected on the silica crucible of the bay, in a silica crucible bay. So what happened that there is this there is a crucible, a cup like a structure, a cup like glassware, which is used to uh, mm, uh, which is used in oven, because we don't want to, in oven that general temperature is greater than 100 degrees Celsius, and we don't want to keep our glass material which is generally used in our lab. So we use a special type of equipment, that is silica crucible, which can withstand a temperature of around 1000 degrees Celsius. Okay now. So the weight of this crucible is 24.802 gram. Both crucible and filter paper were dried for 24 hour on oven at 10 degree 4 Celsius, 104 degree Celsius. Okay now. So post drying, the weight of the filter paper and the crucible was measured as this much and this one respectively. So what happened then? The question is, first you have to understand what is happening here. So we know that our system contains some kind of solid. Our water contains some kind of dissolved solid, suspended solid. Okay now. So we took 100 ml of sample. We took 100 ml of sample, And what we did that we passed this we took a filter paper, and we did some arrangement, and we passed this water through this filter paper. The diameter of this filter paper is generally 0. Uh, I don't know, 0.44 micron. That micron means 10 की power minus 6 meter. Okay na, 10 की power minus 6 meter. The pores the size of the pore of this filter is okay na. So we pass this water, and now what will happen that the suspended solid which is there will remain on the surface of this filter, and what will happen that all the dissolved ion will go to the bottom of this equipment. So what will happen that now we will collect this filter paper containing suspended solid, and we will be keeping it in a dry oven at a temperature of 104 degrees Celsius at 24 hours. So initially I have measured it. It was coming out to be 1.750 gram. After 24 hour, we measured it, and we found out that the weight was 1.92 gram. So the mass which has settled at the surface of the filter paper, which kind of mass will be this one? This one will be all the suspended solid which was in the system, which was there in the water, has come on the surface of this filter paper, and upon drying all the water was evaporated, and the mass which will be getting by subtracting this value and this value, because the mass of the filter paper will be constant, that is 1.75. So the solid which was get has been collected uh, at the at this surface will be my suspended solid, that is 1.7 sorry 1.92. So this is this question was there, that uh, uh, question is, find the total suspended solid. Total suspended solid means how much suspended solid is there in system. And how we have found out suspended solid? We have passed our sample through the filter paper, and all the suspended solid was on the surface of the filter. Okay na. So mass of the blank filter was 1.75. Mass of the mass after dry oven, mass of the filter paper was 1.92. So the total solid retained on the filter after drying oven will be 1.92 minus 1.7, and the total volume was 100 ml. So it will be 1740 milligram per liter. So this is our total suspended solid. So you have to just remember that how much was settled at the how much mass was retained on the surface of the filter paper, and upon and we know the mass of the filter, so we can just subtract it, and we can find out the suspended concentration of suspended solid. Okay now. Similarly similarly what happened that for crucible, now this water was transferred to the crucible. Okay na. And this crucible was also kept at 104 degree. Post drying, the weight of the filter, therefore the both crucible and the filter were placed in muffle furnace for 20 minutes. So if you have gone through the lectures, you must be knowing that the, uh, uh, we use muffle at this temperature. See, now our solid will be, there will be two type of solid. One solid will be volatile solid, and one will be fixed solid. Okay na. Volatile solid generally contains some kind of carbon. So volatile means that can easily vaporize. So at 550 degree, what will happen that most of the carbon which is there at this much high temperature, it will combine with O2, and it will form it will form CO2. It will form CO2, and volatile, yeah, vaporize. So that's why when we have to find the total volatile solid and total fixed solid, we use the we keep our sample at 550 degrees Celsius, and after treatment. So remember these two temperature, 104 degree, 104 degrees to find the total suspended solid, and 1550 is to find the volatile solid. There is one more important temperature, that is 180 degrees Celsius, and 180 degrees Celsius is used to find the dissolved solid, which is not in this question. But remember, 180 degrees Celsius is used to find the dissolved solid. Okay, now. So given the all the value, now the next question is total volatile suspended solid. So we know that volatile suspended solid will be whatever now what has happened that mhm, all the all the suspended solid which was there has was on this filter paper. Okay, so this will contain both volatile and non volatile. So this will contain both volatile and non volatile. So now if I have kept it at high, suppose at 550 degrees Celsius, so all the volatile solid will vaporize, so and remaining will be fixed solid that cannot be vaporized. So difference of these two will give us the concentration of suspended solid, volatile solid. So this has been done. The VSS is solid lost on ignition on filter paper. After keeping at 105 degree, it was 1.924 degree, and after after keeping at 550 degrees Celsius, the mass was this much. The difference of this will be giving the volatile suspended solid. Okay, and the final question is, what is the total solid? Hmm. So remember, one thing is written in the question itself is written incorrectly, that this crucible was kept at 104 degree Celsius. This crucible was not kept at 104 degree Celsius. This crucible was kept at 180 degree Celsius. That's why they have we have used this solid written on the crucible after oven drying to find the total dissolved solid. Okay, now. So remember, all the solid which was there in the sample will be suspended solid plus dissolved solid. Okay, now. So suspended solid we have find out at keeping at 105 this, for this I have used 104, and for this I have used 10 180 degree Celsius. Okay, now. So huh. So you can see that the way after oven drying, after oven drying it was 24.928, and after oven drying the empty weight of the crucible weight was 24.80 degree. The difference will be between these two will be this much divided by 100 ml, and I have converted into 1260 100. Remember, ml 1 ml 1 ml is equal to 1 ml is equal to 10 की power minus 3 liter, 10 की power minus 3 liter. Okay, so the total solid will be total suspended solid plus total dissolved solid. So I think I have said, because time is limited, and I have said it in a very fast way, but I will ask you to go to chapter number 26 of this book. 26. Go to the chapter number of 26 of this book. You will getting a very good idea of what I was saying. Okay, now. The book name is this much. Take a screenshot of this book, Chemistry for Environmental Engineering and Science by Sawyer and McCarthy. Just take a screenshot. Whatever I was saying can be found in this book. And You can download it from internet. Just search for chemistry for environmental. Just search for this thing. You will get it. Chemistry. See this. Just search free PDF. Mm-hmm. Yeah. See, I'm just sharing the link. Can I get PDF, sir? Is the lecture based on environmental? Yes. All the lecture are based on environmental engineering. Means wastewater treatment. We are talking about wastewater treatment. That's why. So you can download it by yourself, or I'm just sharing one link. You can just let me check. Is it is the same book now? No, this is not. This is different book. I think this one. You can. You can download it from here. I'm sharing you the link. Please download it from here. Just copy this link. Once you have copied it, just tell me because I have to go. You can. Or if you are not able to download using this link, just search like this and go through some of the link. You will be able to find the book. Okay, na. But please read this book. Whatever is being taught, whatever I am discussing, I am taking help of this book only. Okay, so I am ending the lecture. See you next week. Tata. Good night.